Numerical Series 9, air of mass 1 kg, initially at 300 Kelvin and 10 bar is allowed to expand isothermally till it reaches a pressure of 1 bar. Assuming air as an ideal gas with gas constant of 0.287 kJ per kg Kelvin, the change in entropy of air in kilojoule per kg Kelvin, round off to 2 decimal places, is dash. So before we start solving the given numerical, let's understand the statement of numerical with the given data. So let's write down the data given in the question. So here the first data is given, that is air of mass 1 kg. So let's consider mass to be m, that is equal to 1 kg. So air of mass 1 kg initially at 300 Kelvin and 10 bar. So here in this question, the initial temperature and pressure is given. So initial temperature, let's consider to be T1, that is equal to 300 Kelvin. And initial pressure, let's consider to be P1, that is given as 10 bar. So now, according to the question, the air expands isothermally. So let's understand the expansion process isothermally according to a coordinate diagram. So let's consider the coordinate diagram to be TS diagram. So here we consider T, that is temperature, along y-axis, and entropy, that is S, along x-axis. So as in the question it is mentioned that the expansion of air is isothermally. It means by keeping temperature to be constant, the air expands here. So here let's consider initially the state of air to be 1, and as the air undergoes an expansion process by keeping temperature to be constant, so after expansion the state becomes 2, and here we can see that the temperature is constant. So as it is an expansion process, it means here we can say that the entropy is increasing. So here it is clearly visible that initially the entropy is S1, and after expansion the entropy becomes S2. And from this diagram, from this coordinate diagram, it is clearly visible that S2 is greater than S1. So entropy is increasing here. So in this question we have to find out the change in entropy. So that is del S. So that is equal to S2 minus S1. So this we have to find out as per the question. So now here we have some more data that is given in the question. So that is the expansion process is continuous till the pressure of air becomes 1 bar. So it means initially at state 1 the pressure is given, that is 10 bar, and after expansion, or you can say that the expansion process will continue till the pressure becomes 1 bar. So as we get 1 bar pressure, so the expansion process stops there. So after expansion the pressure becomes P2, and that is given as 1 bar. Next data that is given here, that is gas constant, and let's consider that gas constant to be R, that is equal to 0.287 kilojoule, 287 kilojoule per kg Kelvin. So now we have all the data given here, and what we are going to calculate here, that is del S, that is equal to S2 minus S1, that is change in entropy of air. So here we have to calculate del S. For that we are going to use the TDS relation. But in thermodynamics we have two TDS relation. One is TDS equal to du plus PdV and another is TDS is equal to dH minus VdP. So we have to select which TDS relation we are going to use here to get the expression of change in entropy, that is del S equal to S2 minus S1. So these TDS relations are further modified into del S is equal to CV ln T2 by T1 plus R ln V2 by V1. So this expression we will get from the first TDS relation. Now by using second TDS relation, this one, we get del S equal to Cp ln T2 by T1 minus R ln P2 by P1. So this is from the second TDS relation. So let's see which TDS relation we are going to use here to get the expression of change in entropy. So according to the data given in the question, we see that the second TDS relation, that is del S equal to Cp ln T2 by T1 minus R ln P2 by P1 is applicable here to get change in entropy of air, because we have here temperature value and pressure value. So this expression we are going to use here to calculate the change in entropy. So let's write down again the change in entropy to be del S equal to S2 minus S1, that is equal to Cp ln T2 by T1 minus R ln P2 by P1. Now in this question we have temperature value, the gas constant and pressure value. So here in this question, as the process is mentioned, that is isothermal expansion, so we can say that temperature is constant. So here we can say that T1 is equal to T2. So in place of T1 we can write down T2, or in place of T2 we can write down T1. So simply if you substitute that as Cp ln T2 by T2 minus R, that is given to with 0.287 into ln P2 is, that is 1, and P1 is given, that is 10 bar. So see, here we don't have the value of Cp, but is it necessary really to calculate this expression? So let's see the ln T2 by T2. So it means it is 1. So the value of ln 1 is 0, so that we know. So if you substitute here ln 1 as 0, so Cp into 0 becomes 0. So here we simply write down 0. So this expression, the Cp ln T2 by T2 gets 0 here, minus 0.287 ln 1 by 10. So after solving this expression, we get it to be minus 0.66 here. Minus minus plus, so it becomes 0.66 kilojoule per kg Kelvin. So we can say that the value of change in entropy for air, that is equal to 0.66 kilojoule per kg Kelvin. So this is the final answer. So this problem showcases how we apply fundamental principles of thermodynamics to real world scenario. I think it is now clear the concept of the change in entropy. Thanks for watching. See you in the next video.